everyone! For today's discussion in statics of rigid bodies, we're going to discuss the introduction to analysis of structures. So for this lesson, students must be able to recite the concept of analysis of structures. Students must be able to identify the difference of truss and frames, and students must be able to identify zero force members in trusses. So let's start our discussion. So we will define first what analysis of structures is. So the analysis of a structure is the process by which we determine how the loads applied to a structure are distributed throughout the structure. The study is limited to pin-connected types. That is, those that consist of assemblages of bars fastened together by smooth bolts. The purpose is to determine the forces acting in the bars and upon the pins or hinges of the structure. Okay, so for analysis of structures, there will be two structures that we will analyze here. Okay, so the first one is the pin-connected trusses and the second one is the pin-connected frames. Okay, so these are examples of pin-connected truss and pin-connected frame. Okay, so for these structures, okay, so these structures are composed, okay, of bars. Okay, so these are the bars. Okay, for this pin-connected truss and for this pin-connected frame, these are the bars. Okay, and these bars are also called members. Okay, so for this truss, this is member AC, member BC, and member AB. Okay, for frame, this is member CE, member FD or DF, okay, and member AB. Okay, and also, for trusses, okay, so the bolts or the pins or the hinges where these bars or members are connected, okay, they are called joints. So this is joint A, this is joint B, and this is joint C. Okay, so previously from our discussion in equilibrium of force systems, we are just solving, okay, for the reactions provided by the support. Okay, so we just solve for the reaction. Okay, here let's say for support here at A, we just compute the reaction here and the reaction here at support at B. Okay, but here in analysis of structures, okay, we are going to compute the reactions or the internal forces acting in the members, okay, and in joints. Okay, so we will analyze, okay, how will these members, okay, these members and these joints, okay, will react from the loads applied in the structure. Okay, let's say for this structure, for this truss, this is there is an applied load P here, and this applied load P, okay, of course, there will be reactions here at the support, okay, but the forces, okay, that will be supported by these supports, okay, it will be transmitted, okay, it will be transmitted by the members and the joints. Okay, so we will determine, okay, those forces, okay, or those internal forces or reactions, okay, that acts in the members and in the joints. Okay, so this is what analysis of structures is all about. Okay, so let's start. So for analysis of structures, it is very important that we know how to distinguish trusses and frames. Okay, so because there are methods here that can only be applied for trusses and there are methods here that can only be applied for frames. Okay, so we will discuss first, no, the difference of trusses and frames. The first one is according to the application of loads. Okay, so for trusses, the loads are applied only, okay, they are applied only at the joints. Okay, while in frames, the loads can be applied within the span, okay, of the members. Okay, so this is the illustration here. Okay, so for this truss, as you can see here, the loads are just applied at the joints. Okay, so we cannot apply the loads within the span of the members in trusses. Okay, it can only be applied at the joints. Okay, while in frames, okay, so this is the illustration for frames. Okay, so the for frames, no, we can apply, okay, the loads here within the span of the members. Okay, so also it is important to know that for trusses, okay, the bars here are attached, no, end to end. Okay, so while in frames, okay, there can be members here, okay, that can be attached within the span of another member. So for this member, let's say this member DF, this is actually attached, okay, within the span of member CE, right? So that is an important difference, no, in trusses and frames. So for trusses, you cannot there are no members here that are attached within the span, okay, within the span of the members. Okay, so that is frame. Okay, that is only for frames that we can attach members, okay, within the span of another member. Okay. Okay, so the second difference between the two structures is according to the actions of members. Okay, so the essential difference between these types is that in trusses, the internal force in a bar is directed along the axis of the bar, whereas in frames, the members are subjected to bending action. So for the members of trusses, let's say for these members, okay, so for these members, the internal force, okay, is directed along the axis of the bar, meaning the bar will be subjected to either compression, it will be compressed, or it will be tensioned. Okay, it will be tension here. Okay, while in frames, the members, okay, can be subjected to bending action. Okay, it will bend. Okay, since the loads in the frames can be applied within the span, okay, within the span of the members, and since there can be members that can be attached, okay, within the span of another member, so that member, okay, will be subjected to bending. Okay, so this is a very important difference also for trusses and frames. Again, for trusses, the members are just subjected to either compression or tension, while in frames, the members are subjected to bending. So we will talk more about trusses here. Okay, so a truss is a structure that is made of straight, slender bars that are joined together to form a pattern of triangles. Trusses are usually designed to transmit forces over relatively long spans. Okay, common examples are bridge trusses and roof trusses. Okay, so trusses, it is also a structure composed of members fastened together in such a way as to resist change in shape. It is a rigid structure, meaning to say, okay, the structure, our assumption here is that the structure will not experience deformation, no? So since the space position of a truss member is fixed by the rigid connection of the truss and the loads are applied only at the joints, a free body diagram of a typical member would show it acted upon by only two equal, oppositely directed forces exerted by the pins at its ends. These forces must be actually directed along the members. So as I've mentioned earlier, okay, the members in trusses are only subjected, okay, to either compression or tension. Okay, so the forces acting on that bar, okay, when it is subjected by compression and tension, okay, those two forces, okay, they should be equal. They should be equal and they should be oppositely directed. Okay, so such members held in equilibrium by only two forces are called two-force member. Okay, so the members, okay, in trusses, okay, are also called two-force members. Okay, so the analysis of trusses is based on the following three assumptions. So the first assumption is the weights of the members are negligible. So we are not going to consider the weights of the members in trusses. Okay, so a truss can be classified as a lightweight structure. Okay, meaning that the weights of its members are generally much smaller than the loads that it is designed to carry. That's why it will just be negligible. Okay, our second assumption here is all joints are pins. Okay, so in practice, the members at each joint, okay, are usually riveted or welded to a plate called a gusset plate as shown in figure B. So this is figure B. Okay, however, if the member at a joint are aligned so that their centroidal axes that pass through the centroids of the cross-sectional areas of the members, intersect at a common point, advanced methods of analysis indicate that the assumption of pins is justified. Okay, so we will assume that all joints here are pins. Okay, so the third assumption here is that the applied forces act at the joint. So I've already mentioned this. Okay, because the members of a truss are slender, they may fail in bending when subjected to loads applied at locations other than the joints. Therefore, trusses are designed so that the major applied loads act at the joint. So this is the reason why we cannot apply, okay, the forces within the span, okay, of the members in trusses, because uh, the members of trusses are slender, no, so they are lightweight. Okay, so if we apply load there, no, it will fail. Okay, it will fail in bending. Okay, so these are the three assumptions, okay, that you should remember in analysis of trusses. Okay, so for trusses, members which are stretched are said to be in tension, while those that are shortened are said to be in compression. Okay, so let's say for this truss, okay, if we get the free body diagram of this member, okay, this is member BD, so this will be the free body diagram of member BD. So this bar or member BD, this is subjected to these forces. Okay, so as we can see here, these forces, okay, are directed this way. Okay, so since this is the direction, okay, of these forces, okay, that acts in this member, okay, so these forces will tend to shorten this member. So meaning to say, this member is subjected to compression. This member is subjected to compression forces. Okay, so also here at member CE, okay, if we get the free body diagram of this member CE, so this will be the free body diagram, and this will be subjected to these forces, and according to the direction of these forces acting on this member, okay, it will tend to stretch this member. So this member is subjected to tension force or to tension. Okay, so if we are going to transfer these forces, okay, from the free body diagram of this member, no, if we are going to transfer this to the free body diagram of the joint, let's say at joint B, okay, so if we're going to transfer this, it will be directed oppositely. So if this is directed this way here, no, if we transfer it in the free body diagram of the joint, so it will be directed oppositely. It will be directed this way. Okay, also for this force, it will be directed oppositely here at joint D. Okay, also for this force, no, it will be directed oppositely here at joint C. Okay, also for this force, it will be directed oppositely here at joint E. Okay, so from these diagrams, we deduce the following rule. A member in tension causes forces which pull away from its end joint. So here at joint C, no, so the member attached here is in tension. So meaning to say, okay, the force here, okay, will pull away from this joint. Okay, it will be directed away from the joint. Okay, whereas a member in compression causes forces which push toward its end joints. Okay, so for joint B, no, the member attached here is compression. Okay, so the force here, okay, will push toward its joint, this joint. No, that's why it is directed toward the joint. No. Okay, so we will now proceed to frames. If some or all members of a pin-connected structure are subjected to bending action, the structure is called a frame. So take note here that if some or all members, so meaning to say, there can be members in a frame that are not subjected to bending action, that are just subjected to compression or tension. Okay, so it can be just some members, okay, that are subjected to bending action, and that is already a frame. Okay, so the members subjected to bending action are three force members. So if in trusses, the members are called two force members just because there are only two forces acting in members. Okay, here in frames, okay, the members subjected to bending action are called three force members. Okay, so a three force member is one subjected to three or more forces applied at different positions. So let's say for this frame, no, okay, so for this frame, there is a member here, okay, wherein there is an applied load P, okay, and this applied load P, this is applied within the span, okay, of this member. So from that, no, we can already say that this is a frame since the load is applied within the span, okay, of the member here, no. So this member, since it is applied or there is an applied load P within its span, so it will be subjected to bending. Okay, since this force P will push this member this way, okay, it will bend like this. No? So, of course, there should be a reaction force, okay, that will oppose that action, that bending action. So, those forces will be these forces or these reactions. Okay, so since we know that this is a pin-connected frame, no, so these are pins, no? So, this is pin, okay, this is pin here and pin here. So, as we know, for pin connections, there are two reactions, one horizontal reaction and one vertical reaction. So, except for trusses, because as we know nga in trusses, okay, the members are just subjected to one force at one end, no, and one force at another end. Okay, and those forces are directed along, no, the axis of the member. But here in frames or in members subjected to bending, okay, there will be reactions here, one horizontal reaction and one vertical reaction. So same here at the other end, since this is already pin connected here, no? So from here, no, as we count these forces acting in this member, okay, so we can count this as 1, 2, 3, 4, 5. So there are 5 forces acting on this member. So this member, okay, is as I've mentioned, this is a 3-force member since there are 3 or more forces applied at different positions, okay, in this member. Okay, so these are the different methods that we're going to use to analyze structures. So for trusses, the methods that we're going to use are method of joints and method of sections. While for frames, the method that we're going to use is method of members. Okay, so we will discuss these 3 methods, okay, in our succeeding discussions in detail. Okay, so before we proceed to our discussion in methods for analysis of trusses, we will discuss first, okay, how to determine zero-force members in trusses. So there are trusses that have members that don't have forces acting on that member. Okay, so those members, okay, are called zero-force members. Okay, so we can determine those zero-force members by using these 2 cases. Okay, so the first case is for 2-member joint or for joints that has 2 members attached to it. No? So for case 2, this is for joints that has 3 members, okay, attached to that joint. Okay, so for the first case, okay, we can determine zero-force members if those members are non-collinear and there are no other external loads or reactions at the joint, then both of these members are zero-force members. So for this truss, this is the example for case 1. So as we can see here, there is a joint here that has 2 members attached to it. So that is joint A. So this joint A, okay, there is a attached member AC and member AB. Okay, so for us to say that these members are zero-force members, it has to satisfy the conditions for case 1. So the condition for case 1, the first one or the first condition, those 2 members should be non-collinear. So in this case, these 2 members are non-collinear, right? And the second condition, there should be no external loads or reaction. So for this joint, no, there is no applied load here, right? And there is also no support here, or there will be no external reaction here because this is not attached to a support like this. Okay, so there are no external load here and there are no external reaction here. So from that, since it satisfied those 2 conditions, okay, so meaning to say these 2 members attached to this joint A are actually zero-force members. So this member AC is zero-force member, and this member AB is also a zero-force member. Okay, so there is also a sub-case here for case 1. Okay, so the sub-case here is if those members are non-collinear and there is an external load at the joint that is collinear to one of the 2 members, the member that is non-collinear is a zero-force member. So there can also be cases that let's say we have here a joint and there are 2 members attached to it, but there is an external load. So let's say the external load is collinear, okay, collinear to one of these members. So let's say we apply a horizontal load here. Okay, that is collinear to member AB. So the member that is non-collinear, not collinear to these 2 members or the member AB and the external load, okay, the member that is not collinear to those two, okay, will be a zero force member. So meaning to say, member AC will be a zero force member if there is an external load, again, that is collinear to member AB. So meaning to say, AC, member AC will be a zero force member. Okay, so that is for the first case. Now, for the second case, this is applicable for joints that have three members. Okay, if two of those members are collinear and there are no other external loads or reactions at the joint, then the member that is non-collinear is a zero force member. So let's say for this truss, so this is an example for case 2. Okay, so as we can see here, there is a joint here that has three members. Okay, so this is joint B, no? This joint B has member BC, member BD, and member AB attached to it. Okay, so if this satisfies, okay, our condition here, so the first condition, okay, two members are collinear. So two members here are collinear. Member BC and member AB are collinear here. And there are no external load. So there is no external load applied here at this joint, no? And there is also no external reaction. Okay, so that satisfies that condition. Okay, then the member that is non-collinear is a zero force member. So meaning to say this member BD, which is non-collinear to the two members here that are collinear. Okay, so this member BD is a zero force member. Okay, so that's how we know or how we can know, okay, the zero force members in trusses by inspection. So this will be very useful because we don't need to compute for those members. We can know them by just inspecting the members in that structure. Okay, so from that we can lessen the computation, no, for the analysis of this structure if we know how to determine zero force members. Okay. Okay, we will now start solving sample problems on how to determine zero force members. So for number 1, we are asked here to determine the number of zero force member for this given truss. No? So for this truss, okay, to determine its zero force members, we are going to apply the two cases, case 1 and case 2. So case 1, that is for two-member joints. Case 2, that is for three-member joints. So we are going to look for joints, okay, from this structure that only have two members or three members attached. No, so we will start with joints that have two members. So let's say for joint B, no, so there are four members here. So there will be no case that can be applied here. Okay, for joint C, okay, as we can see here, there are only two members here, no? So we can apply case 1, but it has to satisfy, okay, the conditions for case 1. So for case 1, okay, the two members here should be non-collinear. So it satisfies that, okay? So um, it should not have external load, no, for case 1, but it can be applicable for case 1.1, but the condition there is that for case 1.1, the external load should be collinear to one of the members. But the external load here, as we can see here, this is not collinear to one of the members here. Okay, so case 1.1 cannot be applied here. Okay, for joint E, so there are three members here, but there is an external reaction here since this is attached to a support, no? So we cannot apply case 2 here. Now for joint D, so this joint D, there are two members here, okay, member BD and member DE. Okay, so we cannot apply case 1 here, but we can apply case 1.1. So since there is an external load here, no, for case 1.1, the external load here, okay, it should be collinear to one of the members. So here it satisfies that condition because this external load, this is collinear to one of the members, which is member BD. So meaning to say, if this is collinear to this member, so the member that is not collinear to these two forces or to these two, no, this member DE will be zero force member. So from here we can already say that member DE, okay, member DE is a zero force member. So that will be the answer for this problem. No, there is a one zero force member here. So that will be the answer, and that is member DE. So we will now proceed to sample problem number 2. Okay, so we are going to determine the number of zero force member or members for this given truss. Okay, so for this truss, to determine the zero force members, we are going to look for joints, okay, that have 2 or 3 members. So for joint A, okay, there are 2 members attached to it, but there is an external reaction here since this is attached to a support, so we cannot apply case 1 here. Also for joint F, there are 2 members here, but there is an external reaction here, so we cannot apply case 1 here. Now for joint C, so as we can see here, there are 3 members that are attached to joint C. So let's see if we can apply case 2. So for case 2, there has to be no external load. So there is no external load here. But there is also a condition that there should be 2 members that are collinear. But in this case, there are no members here that are collinear, right? So there is no zero force member for joint C. Okay, now for joint B. Okay, for joint B, there are 4 members here. So neither of the 2 cases can be applied here. For joint E, okay, there are also 4 forces here or 4 members here. So we can neither apply case 1 or case 2 here. Now for joint D, okay, there are 3 forces or 3 members attached to it, no? So let's see if we can use case 2. But in case 2, there has to be no external load. So that satisfies that. But also, one of the conditions for case 2, 2 members should be collinear. Okay, so there are no members here that are collinear. So meaning to say, there has no zero force member. There are no zero force member for joint D. Okay, so all in all, for this truss, no, for this given truss, there is actually no zero force member. So that will be the answer for this. Okay, for number 3, we are going to determine the number of zero force members for this given truss. Okay, so for this truss, no, to determine the zero force members, we are going to look for the joints that only have 2 members or 3 members. Okay, so for joint A, obviously, there can be no applied case here because there is a external reaction here. Same with joint G. Now we proceed to joint B. So as we can see here, this joint B has 3 members attached to it. So let's see if we can apply case 2 here. So for case 2, there should be no external load. Okay, so that is checked for that. No, there is no external load here. And there has to be 2 members that are collinear. Okay, in this case, the members that are collinear here are member A, B, and member BC. So meaning to say, the member that is not collinear to those 2 members is zero force member. So member BH is already a zero force member. Okay, so BH is a zero force member. Okay, so if this is already a zero force member, okay, here at joint H, no, if we know already that BH is a zero force member, there will only be 3 members here: member AH, member HI, and member CH. No, so here we can also apply case 2 here, no, since the 2 members here are also collinear, so the member that is not collinear will be a zero force member. So member CH, okay, is a zero force member. So from that, if we proceed to joint C, okay, if we proceed to joint C, there will only be 3 members here since we already know that CH is 0. So the members here will be BC, CD, and CI. Okay, so as we can see here, we can also apply case 2 here since there are 2 collinear forces, members here, member BC and member CD. So the member that is not collinear to those 2 members is a zero force member. So member CI is a zero force member. Okay, so if we proceed to I, again, there will only be 3 members here if we know that CI is a zero force member. And we can also apply case 2 here. 2 members here are collinear. So the member that is not collinear to those 2 members will be zero force member. So member DI is also a zero force member. So from that, no, if we proceed to another side of this truss, no, we can also know that member FL is a zero force member, member EL is a zero force member also, member EK is also a zero force member, and member DK is also a zero force member. Okay, if these forces or these members are zero force members, okay, if we proceed to joint D, the forces, the members attached to it are just CD, DE, and DJ. No? So, if we apply case 2 here, two members here are collinear. So, this member that is not collinear, which is member DJ, will be a zero force member. So, member DJ is also a zero force member. So, if we count those zero force members, okay, so from that, no, those are already the zero force members for this truss. So, this is 1, 2, 3, 4, 5, 6, 7, 8, 9 zero force members. So for all these joints, no, we applied case 2, no. So we determined here by inspection that there are 9 zero force members in this truss. Okay. So that concludes our discussion for this topic. But don't just go yet, because I am giving an additional point or a bonus point for those students who will comment their name, their section, and the concept that they learn, okay, from our discussion about analysis of structure. So you just have to give one concept, okay, that you learn from this discussion. Okay, the first five students, okay, who will comment, okay, will receive those bonus points. So I hope that you see this, no? Sayang ito, class. Bye-bye. God bless. Keep safe.